This is assignment 2 for engineering materials. Our metals were copper and palladium by Caleb, Jack, and Travis.
Alright, for our first question, it was finding the crystal structure of copper and palladium. So copper and palladium both have a face cubic center structure, FCC. 4 atoms total in one unit cell, 8 corners times 1/8 equals, and then plus 1/2 atom times 6 sides gives us 4. Every face has a center atom. Softer metals usually have a face center structure. Alright, and for our semiconductors, we did aluminum nitride and aluminum gallium nitride semiconductors. Both have a hexagonal closed pack structure, HCP crystal. 6 atoms total in one unit cell. So that's 1/6 of an atom times 12 equals 6. Most efficient atomic packing factor, meant for harder and stronger materials, more resistant to slip.
Question 2 for the assignment was looking at the coordination number and the atomic packing factor for copper and palladium. So as Jack said in the previous slide, both of these are face-centered cubic structures, and the coordination number, or the number of closest neighbors for face-centered cubic structures, is 12. You can see that in the picture to the right. There are 12 yellow atoms surrounding the center purple atom, so that's why the coordination number is 12. And then looking at the atomic packing factor for copper and palladium, it is the number of atoms times the volume of atoms divided by the volume per unit cell. So as you can see in the lower right hand picture on the screen, we're saying A is the length of one of the sides of the cube. So for face-centered cubic, the number of atoms is 4, as Jack mentioned in the previous slide. The volume is equal to 4/3 times pi times r cubed, and the relationship of r and a in face-centered cubic is radical 2 divided by 4. So the volume per unit cell, that's just equal to the volume of a cube, so that's a cubed. So the atomic packing factor for this would be 8/3 times pi times radical 2/3 squared, which is equal to 74%. So the third part of question 2 was looking at the theoretical density for palladium and copper. So for theoretical density, the formula is number of atoms per unit cell times the atomic weight divided by the volume per unit cell times Avogadro's number. So the number of atoms per unit cell is 4 again. The atomic weight for palladium is 106.42 grams per mole. The volume per unit cell, so that's again A cubed, and then in face-centered cubic structures, A is equal to 4 times the atomic radius divided by radical 2. And for palladium, this is 1.39 times 10 up to the -8 centimeters. So altogether, the volume per unit cell is 6.03 centimeters cubed. And then Avogadro's number is 6.023 times 10 up to the 23rd. So combining all these into that theoretical density formula gives you 6.95 grams per centimeter cubed. So looking at this for copper, again, the number of atoms per unit cell is 4. The atomic weight for copper is 63.55 grams per mole. The volume per unit cell is 4.75 times 10 up to the -23 centimeters cubed. And then Avogadro's number is again 6.023 times 10 up to the 23rd, and then the theoretical density, after putting all those into the formula for copper is 8.89 grams per centimeter cubed.
Question 3 for our assignment was to show the crystalline direction family of 120 and the crystalline plane family of 111. As you can see here, we have the crystalline direction family of 120, which could be represented as a square sheet that goes 1/2 on the x-axis and 1 on the y-axis with nothing on the z-axis. When plotting it, you can have intercepts at 1/2 a, 1b, and infinity. Once you have that, you can get the integers, which are 1/2, 1, and infinity. You get the reciprocal of those integers. You will get 1, 2, 0, and they're already at their smallest integer, so that is how you can get 1, 2, 0. And then the family for the crystalline direction could be represented as 1, 2, 0, -1, 2, 0, 1, -2, 0, and -1, -2, 0. Here we have the crystalline plane family of 111. The crystalline plane family of 111 could be represented as a triangle sheet that goes to 1 on the x-axis, y-axis, and the z-axis. When drawing the family for this, you can get your intercepts at 1a, 1b, and 1c. From that, you can get the integers 1, 1, 1. You take the reciprocal of those, and it's still saying is 1, 1, 1, and they're already at the smallest integer. So that is how you would get 1, 1, 1 for the crystalline plane family. The family for this crystalline plane is represented as 1, 1, 1, -1, 1, 1, 1, -1, 1, 1, 1, -1, -1, -1, 1, -1, 1, -1, 1, -1, -1, and -1, -1, -1. The second part of question 3 was to calculate the linear density and planar density of our atoms in our metal A, metal B, and our semiconductors A and B. The linear density can be calculated using the equation LD is equal to the number of atoms divided by the length. The linear density for our metals and semiconductors were 3.906 atoms per nanometer for copper. For palladium, it was 3.65 atoms per nanometer. For aluminum nitride, it was 6.93 atoms per nanometer. And for aluminum gallium nitride, it was 8.197 atoms per nanometer. You can see in the bottom right how it was calculated. To calculate the planar density, you would use the equation planar density is equal to the number of atoms divided by the area. The planar density for our metals and semiconductors were, for copper, it was 15.26 atoms per nanometer squared. For palladium, it was 13.32 atoms per nanometer squared. For aluminum nitride, it was 13.179 atoms per nanometer squared. For aluminum gallium nitride, it was 19.39 atoms per nanometer squared. You can see how they were calculated in the bottom right. In conclusion, since copper and palladium both have face-centered cubic structures, they're going to have similar properties and are going to be similar in theoretical density, linear density, and planar density calculations. The semiconductors, aluminum gallium nitride and aluminum nitride, both had similar crystal structures. Both of them were HCP. So both are going to have similar linear density and similar planar density.